If you were to go to a shopping mall and ask random women as they walk past you what their height would be, let's say you ask 200 women, and each time you stop somebody, you put a dot on this little dot plot here. You would notice, I'm not going to do 200 dots here, but you're going to notice that you're going to have some outliers, women that are taller than usual and some shorter people. You're going to notice that most of the data is going to have a peak here. And in statistics, there is a shape called a bell-shaped curve. It's also called the normal distribution. And you're going to notice that it's going to be very, very symmetric if you ask, 100 or 200 women. And actually, the more women you ask, the more bell-shaped and symmetric it will become. And it is a phenomenon in statistics known as the normal distribution. And suppose those 200 women, you calculate the average height, and you get 64 inches, and you get a standard deviation of 2 inches. Okay, so notice I'm using X bar, that's called the sample mean, and I'm using S here, that's called the sample standard deviation. Now the sample mean, the mean or the average, this is a measure of center. So 64 kind of gives us an idea of what the average woman, what her height would be. And 2 inches is, the standard deviation is a measure of spread. So it tells us that the spread between the dots is about 2 inches apart. So once again, the average is a measure of center, and the standard deviation is a measure of spread. It gives you an idea of how the data is laid out. Now, if we talk about the population of all women, I'm going to be using a Greek letter called mu. Mu is the population average, okay? X bar is the sample mean. Whenever you use a Greek letter here, that's called the population mean. And the population standard deviation is the Greek letter S. And this is a well-known fact. It is known that the height of women is normally distributed, and it has a mean of 64.5 inches and a standard deviation of 2.5 inches. So we would say that the women's heights are normally distributed. And let me share with you a fact about the normal distribution. Now this goes for any data that is normally distributed. There's something called a 68, 95, and 99.7 rule. And what that says is that, if we take our women here, our women example, so the average woman is 64.5 inches. And we would say that 68% of all women falls within one standard deviation of the mean. So what that means that if the standard deviation is 2.5 inches and I add 2.5, to the mean, that gives me, let's see, 67 inches. And I subtract one standard deviation to the left of the mean, that would put me at 62 inches. We would say that women between the heights of 5'2", which is 62 inches, and 5'7", 68% of all women are between that height, okay? Now the area underneath this curve here is equal to 1, or 100%. So the total area under the curve is 100% of all females. Notice that it never touches the x-axis because it leaves room for a really tiny woman, and it leaves room in the upper tail for an extremely tall woman, okay? So it never touches the x-axis because there's always room for outliers in there. Now, that's the 68% rule. So the nice thing about this normal distribution is that the area under the curve is equal to the percentage or the probability of these measurements, okay? Now, if we go 2 standard deviations from the mean, Oh dear. Let me get that picture back. Hang tight. All right. So if I wanted to clear all the strokes there, it was getting messy. So if we take the standard deviation of 2.5, and we're still at the average of 64.5, the 95% part of this rule is that's 2 standard deviations away. So if I take 2 standard deviations gives me 5 inches, which means if I add 5 inches to 64.5, that gives me 69.5 inches. And if I subtract 5 inches from that, that gives me 59.5 inches. So that's 4 foot 11.5. Okay. Now, 2 standard deviations of the mean is 95% of all women are in that interval. Okay. And then, of course, the 99.7 rule is 3 standard deviations away. So if we add 3 standard deviations to the right of the mean and subtract 3 standard deviations to the left of the mean, that is almost 100% of the whole population. So that leaves room for 0.3% of gals that are really, really tall over here and gals that are really, really short over here. Now, so just a little bit of understanding here before I move on to a harder example. If 95% of all women are 2 standard deviations from the mean, so this is 95% right here, that leaves 2.5% in this little green tail here. Okay, 2%, 2.5%. Okay, not to be confused with our standard deviation of 2.5. This is 2.5% of the population. And in the lower tail is also 2.5%. Okay? So look, we got 2.5% here, 95% here, and 2.5% in the upper tail, which gives us 100% of the population. So to just make some conclusions here, I could say, switch to blue, I can say that 2.5% of all women are taller than 5'9.5", 69.5 inches. I can equally say that 2.5% of all women are shorter than 59.5 inches. Just by that symmetry there, the tails have equal probability. Okay, so this is all clean when you have nice whole standard deviations, like 1 standard deviation to the mean, 2 standard deviations to the mean, 3 standard deviations from the mean. But what if you are, let's see, this height is 1 standard deviation from the mean. This is 67 inches right here. Okay, so we got 67 inches here, and we have 69 inches here. What about 68 inches? What percent of all women are taller than 68 inches? So it's not that easy because 68 inches is not a whole standard deviation away from the mean. So what I'm trying to do is I'm trying to set a stage for a little formula called a Z-score, okay? And this Z-score, if you're in AP statistics, you're going to be doing the Z-scores for about 8 months out of the school year. In the IB program, the International Baccalaureate, it's about 5 to 10% of the curriculum in IB math studies. So you're going to be using Z-scores a lot. The nice thing about it is what I'm teaching you now is applicable in AP Stat. It's usually like in Chapter 2. It's very early on in the AP Stat book. It is in also the IB curriculum. Okay? So I'm trying to cover both bases here. And in a bit, I'm going to be showing you an example from the 2014 IB Math Studies test. But before I do that, let's go back to this standard deviation stuff and the normal distribution. So let me do a couple examples with you. So we know that the mean, notice I'm going to use the population mean, is 64.5 inches. And the standard deviation is 2.5, okay? Now, 63 inches is not a whole standard deviation away from the mean. If I do 2.5 take away 64, which is 1 standard deviation from the mean, that puts me at 62 inches. But I have 63 inches here. So I want to know how many standard deviations is 63 inches away from 64. So let me unveil to you what's called the Z-score. And the Z-score is simply you're going to subtract two numbers and you're going to divide by one number. In the denominator, you always put the standard deviation. Okay, so you're going to be putting 2.5 in this case. In this blank here, you're going to be putting the mean, the population mean. So that's going to be 64.5 inches. Okay. And in the first blank, we're going to put the number here that's given to us. Now, when I do 63 minus 64 divided by 2.5, this gives me negative 0.6. So what this means is that 63 inches is 0.6, a little bit more than a half standard deviation away from the mean. It's not a whole standard deviation from the mean. This would be one whole standard deviation. It's about right here. But notice I can't use this rule with that because it's not a whole standard deviation. I got this little fuzzy area here. So we calculate a Z-score, and there's something called a Z table. And I suggest if you don't have one in front of you that you find a Z-score, a hard copy of a Z table. The Z table is two-sided. It has a side with positive Z-scores, and it has a side with negative Z-scores. Okay, now this one looks kind of funny because on the problem that I just did, I got a Z-score of negative 0.6. That puts me right here. Okay, so if I reference the table here, that gives me 27.43%. Okay. So, to put this on my graph, a girl, or a woman, excuse me, that is 63 inches tall, 63 inches tall, would be right here, okay? So we got the mean or the average, which is right down the middle at 64.5, okay? A 63-inch woman is right here. And the probability of someone shorter than that is 27%. So let's go back. The answer to this would be 27.43%. So I move the decimal over two places. Okay, now, what's the probability that a woman is at least 63 inches? So in this case, we're talking about someone that is taller than 63. This one's talking about someone shorter than 63, okay? The good news is that the Z-score is calculated the same exact way, 63 minus 64.5 divided by the standard deviation. It still gives me negative 0.6. That's a negative sign there. Except notice the word is at least, which means 63 inches or more. Okay? Now here's where you're going to have to be very aware of what you're trying to do here. This table only gives you the area less than the Z-score. So if you look at this, the thing is shaded to the left. We want the area to the right, someone that is taller than 63. So if the probability that someone is less than 63 is 27.43, the probability that someone is taller than that, we're just going to subtract that from 100%. So we're just going to subtract that from 1 because remember the area under the curve is 100%. To the left of the Z-score, to the right of the Z-score have to add up to 100. So I'm approximating that is about, what, 73%, 72.5%. So this right here would be about 72 62.5%. Okay. All right, so let's do this one more time with a really ugly number here because there's something in the table that I need to show you. Probability that a woman is taller than 68.33 inches. I chose that height because it's going to give me a really ugly z-score because there's something that I need to show you in the table. So here we go. We're going to calculate the z-score. And you'll always be given the mean and the standard deviation when you do these problems, okay? So they're going to tell you in the body of the question, the population is normally distributed with a mean of and a standard deviation of, okay? So most of the time you're going to be given that data and you just have to find these z-scores and reference it in the table. So now when I do this, it's going to give me a z-score of, let's see, all right, so the top will be 3.83 divided by my standard deviation of 2.5, and this yields a z-score of 1.532. 1.532. So again, this means someone that is 68.33 inches is 1.532 standard deviations away from the mean. Notice we got a z-score that is positive this time. That's because 68 1/3 inches is taller than 64.5. So if you have someone that is bigger than the mean, you're going to have a positive z-score. Someone that's shorter than the mean will have a negative z-score. So that's why you have two sides to that table. So let's find the probability because this is just the z-score. So 1.532. So we're going to go to the z table, 1.532. So here's 1.5, and then, so we got a z-score 1.532. Now this goes to the hundredths place. This is the hundredths place here. The 2 here is smaller than 5, so we're going to just keep it at 1.53. So 1.50, 1.51, 1.52, 1.53. So that's the hundredths place. So a z-score will give us the probability of, so the area in this curve here is, and from here on out I'm going to write the probabilities as decimals, not percentages. It's proper math etiquette in AP Stat and IB to write your probabilities to 4 decimal places. You don't have to convert to a percentage, just leave it like that because it's more accurate. So 1.53 gives us 0.9370. Let's go back to the question. Now it says taller than that. 970, okay. Now let's think about this. If someone, I have students all the time that are just not paying attention and they find the z-score correctly, they got everything set up fine, they look at this at the table and they write down as their answer. And if you think about it, aren't people, so you're saying that 94% of the population is taller than about 5'8.5". The average female is 64.5, so that's 50%. So you're saying that they're taller than that? So what you need to remember is that if the verbiage in the question has at least or more, taller than, you're always going to subtract from 1. Okay, so think greater than, taller than, at least, or more. Those phrases, you're always going to subtract the number from the table from 1. So the true answer to this is going to be 100% minus 0.9370, which gives us about, let me just do it with my calculator here real quick. All right, so about 6% of all women are taller than 68 1/3 inches, okay? All right, so let's go to, we got our little tables here. I'm going to erase all these strokes for another question. And we have these guys here. All right, so in 2014, if you need a pause and go get a snack, I suggest you do that. So that whole thing with the women's height was just my introduction. It gets a little bit harder with this example, but not much, okay? So I'm trying to explain to you not only how to do these questions, but a lot of theory. I'm only making one video on the normal distribution. I'm trying to squeeze everything in there and cover all the bases, all right? So in 2014, the International Baccalaureate decided to put the normal distribution in the curriculum, and this was the first year that they included it in there. And so on paper 2, they had a question about our friend Heejin. They'll mention the name later. Anyway, this question's got about 5-6 parts to it, so hang tight in there. A group of candidates sat in a chemistry examination and a physics examination. So we got 2 different tests. The candidates for the chemistry examination are normally distributed, so they're tipping you off right there that this is symmetric, that rule and the Z-scores all apply. And we have a mean of 60 and a standard deviation of 12. Okay, so draw a diagram of this situation. Well, the normal distribution is bell-shaped. At the dead center would be the mean. And we're going to add 1 standard deviation to the right of the mean, which would put the scores at 72 and the scores here at 48. Okay. If we do 2 standard deviations, we're just going to add 12 one more time to get 84. And we're going to subtract 12 again to get 36. And we're going to add another 12 here to get 96. And subtract the number 12 here to get 24. So if we use the rule that we talked about here, 68% of all the scores are going to fall between 48 and 72. 95% of the scores are going to be between 36 and 72. Okay. And about 100% of the scores are going to be between 24 and 84. Okay. 99.7. Sure, there's going to be, all the way out here. I did that wrong. I hope you caught that. I'm not going to do this video all over again. So here we go. We got 1 standard deviation from the mean. That's the gold. 2 standard deviations go way out here. Okay. So 95% are going to be between 84 and 36. All right. And 3 standard deviations from the mean. 1, 2, 3. 1, 2, 3 to the right. 99.3% of the scores are going to be between 24 and 96. So that would be a little diagram showing the understanding that this is, we got the dead center, okay, at 60, a score of 60 is right there. And if we shade to the left of that, that's 50% of the data. So we would say that 50% of the data, 50% of the scores were less than 60, 50% of the scores were greater than 60. So that's just part A of the question here. The second part is, write down the probability that a randomly chosen candidate who sat at the chemistry examination scored at most 60 marks. There's 2 different ways to do this. You can just find the Z-score. Here's 60. And the mean is also 60. And the standard deviation is 12. Well, we get a z-score of 0. So if we got 60 here at the mean, a score of 60, excuse me, a score of 60, 50% is going to be less than that, okay? So notice question B is just kind of really quizzing you on your basic understanding. If you know that you have a z-score of 0, that's at the 50th percentile. And I want to show you on the z-table where you can also figure that out. So z-score coming right up. My table is here. Okay, so look, we got a z-score of 0, and by golly, there's 50%. Okay, so if we have a z-score of 0, z-score of 0, there's 50%. Okay? All right, so that is part B. So the first two are just very introductory questions. Part C, now it gets a little bit more fancy here. Now, Heejin, she scored 80 on the chemistry exam. And notice we got 60 here. I'm going to draw the picture one more time. Here's 60. One standard deviation to the right is 72. One standard deviation, or two standard deviations to the right would be 84. So this is one standard deviation plus 12, two standard deviations plus 12. So, but notice that Heejin, she scored 80. So that puts her about right here, okay? Now we know that this is 50% over here. To the left of 60 would be 50%. And it's saying more than Heejin. So that would be this area up here, above to the right of 80, this area here. So I don't know, I'm guessing 10%, 5%. It's going to be small though, because she is kind of far, she's almost 2 standard deviations from the mean, but not quite. So what we're going to do is we're going to find her z-score for 80. So z, 80 minus 60 divided by 12 gives us a z-score of 1.66. Okay, I'm going to round that up to 1.67. Okay, because the z-table goes to the hundredths place. This is a 6, so we're going to round up. So 1.67. Here's 1.6, 2, 3, 4, 5, 6, and 7. 1.67. So that's 9525. 9525. So this area here, so the area we get here is 9525. Okay? Now if you're not paying attention, you're just going to write down 0.9525. But this is saying more than. We want the area to the right of the z-score. The z-table only gives area to the left. You have to remember that, otherwise you're going to get these answers incorrect. If you draw a picture of it, you'll never forget, because if you write down 95% and you draw in this little area here, it doesn't match, okay? So what we're going to do, since we're talking about more than, notice that the word more is bold, because they're trying to remind you, look, more than Heejin, not less than, okay? So we're going to take 1, which is 100%, and we're going to subtract that number there to give us 0.0475. Okay, so roughly 5% scored better than Heejin. We would say that Heejin, she is in the top 4, almost 5%. Okay, now that's part C, and we are approaching 30 minutes on this video. All right, now the candidates marks of the physics examination. So the mean for the physics is 63. Because remember, there's 2 different tests. There's a chemistry test and a physics test. The physics mean is 63, and the standard deviation's 10. The chemistry was 80 for the mean and 12 for the standard deviation. So Hee-Jin also scored 80 marks on the physics exam. Here's the word less, so we don't have to subtract from 1 after we reference the z-table. So we're going to find the probability that a random student scored less than Hee-Jin. So we want to know this person's we want to know Hee-Jin's z-score for this one. Now we're going to use 80 because she scored 80 on the physics and the chemistry, except this mean is going to be 63 and this mean is going to be 10. In the previous example, this number here was not 63 and this one was 12. So we have a z-score of 1.7. That means that 80, Hee-Jin on the physics exam scored 1.7 standard deviations to the right of the mean. We know it's to the right of the mean because it's a positive z-score. So here we go, 1.7. We're going to go back to our table. 1.7 is right here. Now, do we have to subtract that from 1? No, we don't, because this is less than. Here's a picture. Here's 63. Here is 80 right here. Here's 80, and we want less than. Look at all that area shaded there. This answer here really makes sense. Okay, so part E. Part E. I'm going to get rid of all these strokes. Okay, I'm going to wrap this up in about 5 minutes. Hang in there. So part E. Can you imagine sitting in a live lecture on this? You wouldn't be able to pause me. You can actually pause me and come back to this if you wanted to. My poor students have to listen to this in one sitting. All right, so here we go. Hee-Jin, determine Hee-Jin's physics mark compared to other candidates. So did Hee-Jin do better in the physics exam or the chemistry exam? You may say, she scored 80 on both of them, but it's compared to the other candidates. So for the chemistry, so this is where the z-scores really come in handy because it gives you a sense of comparison on how you compare with the other people relative to the other people who scored on the same exam. So here's chemistry, here's physics. Now we've already found Hee-Jin's z-scores for both. So 80 minus 63 divided by 10. And that gave us a z-score of 1.7. Now when we did it with the chemistry test, the average for that was 60 and the standard deviation was 12. The z-score with that was 1.6666. So even though Hee-Jin scored an 80 on both tests, 80 and 80, she scored compared to other candidates, she's 1.7 standard deviations from the mean, and this one is 1.667 standard deviations from the mean. So we would say that she did better on the physics test compared to the other candidates because her z-score is farther away from the mean. Okay, so notice they had Hee-Jin score an 80 on both tests on purpose to show you that you'd say, because the common person would say, well, she scored the same, got an 80, okay, on both exams, but the standard deviation is smaller here, and the mean is larger here. So it's hard to compare without doing this little z-score business. All right, last question here. Here is where we have to work backwards. So it says to obtain a grade in A, to obtain a grade A, a candidate must be in the top 10% of the candidates who sat for the physics examination. So in this case, find the minimum possible mark to obtain a grade A. Okay? Now the Z-score, this is how it's set up. Okay? You're going to want to memorize that and know it very, very well because you're going to be doing it over and over and over again. Now the Z-score is not the probability. Okay? The Z-score gives you a probability when you reference it in the table. So this 10% doesn't go anywhere in this little formula. Okay? So, physics examination. The mean is, I'm going to set up all the information that I do know, and it'll become clear. It'll become clear what you need to do here. All right? So, follow me here. So, in this case, we want to know what score do we need here Now, I'm not going to put 10% here because this is a Z-score, not a percentage. So listen, it says top 10%, okay? So we want this on the normal distribution. We want 10% to go here, which means we have to find the Z-score that will give us 90% here, okay? Because remember, the Z-score table only gives you the area to the left of the Z-score. So what's this little Z-score that will give us 90% to the left of it, which will also give us the 10% in the upper tail, okay? So the number one mistake I see people make is they would put the 0.1 here, or they would put it here somewhere, okay? So we're going to go to the Z table, and we want 90% here. Top 10% is here. 90 and 10 make 100%. What Z-score gives us this area? So even though the problem says top 10%, I'm actually going to go hunting in here for 90%. So here we go, here we go. This is the closest one. So 1.2, 1.28. So in other words, 1.28 is the Z-score that gives you 90% to the left of it, which will give us the top 10% in the upper tail. 1.28 is going to go right here. As far as IB is concerned, this is as hard as it gets. In AP statistics, it builds on this little formula, but in IB math studies, this is kind of the end of the road, or the highest skill that you can possibly demonstrate. So we're going to cross multiply here to get 15.36. We're going to solve for question mark. That gives us 75.36. So that's the mystery score that they're referring to. All right, so find the minimum possible score. All right, now it says to the nearest integer, so we would say a score of 75. We would round that up to 75. So let's interpret this answer. Someone who scores 75 would have a Z-score of 1.28, which referenced in the tail would give you 90%. For the lower tail, the upper tail would be the top 10%. Okay? So, good luck to you, and yeah.